This is the video for accelerated geometry on section 9-3 on fitting to a normal distribution. Key vocabulary in this section is standard normal value. The central question is, how do you use tables to estimate areas under normal curves? The standard normal values is calculated and it's what we call a z-score, which the formula is z equals x minus mu divided by sigma. The x, this x is just the number that you're trying to find the association with. Mu is your mean, and sigma is your standard deviation. The area under the curve between x equals a and x equals b is just equal to the area between the standard normal values of a and b. So what we're going to end up doing is finding a z-score, and wherever that z-score is located, remember that the z-score is always the area to the left, so it's always the less than value. So if I find out that this number right here, say this z-score right here was 1 point, I don't know, 2, then whatever this area is would be the value for the probability that the number is less than or equal to 1.2. As far as the percentages go for the normal curve, we have our normal curve. It's made by making the mean in the middle. Your mean is always going to go in the middle here. Then to get the numbers to the left and to the right, you're going to add and subtract standard deviation. So if I go to the right, I'm going to add a standard deviation, go to the right again, you're going to add another standard deviation, go to the right again, you're going to add another standard deviation. And then from your mean to the left, you're going to subtract a standard deviation, subtract a standard deviation, subtract a standard deviation. Now, if we're dealing with numbers that actually fall on the bell curve, so we're talking about numbers that are at these interval lines, then we can use the percentages that you see right here. In between the mean and the mean plus 1 standard deviation is 34%. Between the mean and 1 standard deviation to the mean and 2 standard deviations is 13.5, followed by 2.35, followed by 0.15. So that 0.15 is this section right here, this little section on the tail. Same thing over here. This 0.15 is this little section of the tail. And if you notice, it's symmetric about the mean. So you have your mean in the middle, and then it goes 34%, 13.5, 2.35, 0.15. And then on the right, or the left side here, again, it goes 34, 13.5, 2.35, and 0.15 again. And this will make more sense to us as we start looking at some examples. Another thing that's going to be useful is what we call our z-score chart. Again, you do not have to memorize this chart. This chart will be provided for you, but you do need to know how to use this chart. So if, for example, you're looking for the value that your z is less than or equal to 1.7. First thing you're going to do is find your positive 1 on this left bar, which is right here. And then you're going to find your 0.7 going to the right, which is right here. So this number would be for 1.7. So the number that we would be concerned with is 0.9554. Now, if you have something that you're dealing with a greater than, remember all of these numbers in this chart are for the less than. So if you're doing greater than, so let's do greater than negative 2.4, for example, then you're going to have to subtract your answer from 1. So first thing we're going to do is find the negative 2.4. So we're going to go to negative 2, which is right here, and then go over to 0.4, which is right here. So that would be the z-score for negative 2.4. But we have to subtract that from 1 because we're worried about a greater than, which would end up giving me 0.9918. So let's put this into some examples so maybe it'll make a little bit more sense to us. The directions say to use a normal distribution has a mean of x bar and a standard deviation of sigma to find the indicated probability for randomly selected x value for the distribution. Now, I do want to go ahead and change this to say a mean of mu, because that's what we're going to be concerned with in this unit, is using mu instead of x bar. But know that x bar and mu both mean the mean. So if I want the probability that some number is less than or equal to my mean plus 1 standard deviation, what I'm going to do is I'm going to go to my bell curve, and I'm going to find the bar that is labeled the mu plus 1 standard deviation, which is right here. And then I'm going to add everything, because it's less than, so it's going to be everything to the left. So all those percentages that you see to the left there, you're going to add them up. So it's 0.15 plus 2.35 plus 13.5 plus 34 plus 34. And when you add all those numbers up, you'll get 84%. Or the other way of doing it is if you're doing all of this, instead of adding all these numbers up, you know this whole thing has to add up to be 100, and these three little pieces are not included, so you could just do 100 minus the parts that are not included. Which would also give you the 84%. Let's try another one. Number 2 says a number is greater than the mu plus a standard deviation. So I'm at this same line, but greater than means everything to the right. So then that's just 13.5 plus 2.35 plus 0.15, which will equal 16%. Number 3 says that what is the probability that our number is between the mean and the mean plus 1 standard deviation. So this one requires two boundaries. So I'm going to put a line on my mean. Move this back up for a minute. Put a line on my mean, and then my mean plus the standard deviation. And when it's written like this just means between. So then what percentage is between those two lines? And it's just 34%. Application problem. Talking about oak trees. It says the height and feet of fully grown white oak trees are normally distributed with a mean of 90 feet and a standard deviation of 3.5. About what percent of oak trees have heights between 86.5 and 93.5? So heights between is saying that I'm really finding the probability that 86.5 is less than or equal to x is less than or equal to the 93.5. That's how we write our between statements. So before I even answer this question, I'm going to draw my standard normal curve. In the middle is always the mean. So in this case, your mean is 90. And then to get the numbers to the left and the right, we're going to add and subtract our standard deviation, which in this case is 3.5. So if I take 90 plus 3.5, that gives me 93.5. And then I'm going to add 3.5 again. So 93.5 plus 3.5 is 97. Plus 3.5 is going to be 100.5. Going to the left, if I subtract, that's going to give me 90 minus 3.5 is going to be 86.5. Subtract again. So 86.5 minus 3.5 is going to leave me with 83. And 83 minus 3.5 is going to leave me with 79.5. So next thing I'm going to do is, just for memory, is to put in our percentages. So I know this is 0.15, 2.35, 13.5, 34, 34, 13.5, 2.35, and 0.15. So then I can put in my bars so that I know which two numbers I'm looking at. So at 86.5, which is right here, and 93.5, which is right here. So the two numbers that are between there are 34 and 34. So if I add those up, I get 68%. Number 5, about what percent of oak or white oak trees have heights less than 97 feet? So this is saying find the probability that a randomly picked oak tree is less than 97 feet. So I'm going to go back to my diagram. 97 is right here. Less than means everything to the left. So I can do 0.15 plus 2.35 plus 13.5 plus 34 plus 34 plus 13.5 and add all those up and I will get 97.5. Or I could just do 100 minus the two pieces that are not included, which would be 2.35 and 0.15, which would also give me the 97.5. Number 6 says about what percent of white oak trees have heights between 83 feet and 90 feet. So 83 is right here. 90 is here. So the probability that 83 is less than or equal to x is less than or equal to 90 is just going to equal the two percentages between there. So 13.5 plus 34, which gives me 47.5%. And I just realized that this number is really number 7. It says, find the probability the randomly selected white oak tree has a height of at most 85 feet. So at most means that or less. So it's the probability that a tree is less than or equal to 85. But if you notice, 85 is not on our curve. Okay, so anytime we have a number that is not on our curve, we're going to go and convert it to a z-score. So if you remember our formula, z equals your number minus your mean divided by your standard deviation. So in this case, we would have our number is 85, our mean is 90, and our standard deviation is 3.5. So when I type this in the calculator, 85 minus 90 is -5. -5 divided by 3.5, and round to the nearest tenth, you would get -1.4. So I'm going to find -1.4, so -1 and 0.4, and the number there is 0.0808. So since we're doing a less than, we know that that's just our answer. So we can either leave it as 0.0808 or we can say that it's 8.08%. Let's try some more. Okay, this is really example 8 and example 9. It says Jamie can drive her car an average of 432 gallons per tank of gas with a standard deviation of 36. Estimate the probability that Jamie will be able to drive more than 450 miles on her next tank of gas. So if I were to draw out the curve here, we would have 432 in the middle, add a standard deviation of 36. That gives me 468. Add another standard deviation. We get 504. Add another standard deviation. We get 540. Going to the left, if you subtract 36 from 432, you get 396. Subtract 36, you get 360. Subtract 36, you get 324. So if you notice, it says, what's the probability that Jamie will be able to drive more than 450? 450 is not on this curve, which tells me I need to create a z-score. So my z is equal to my number minus my mean divided by my standard deviation. So z equals the number, which is 450, minus the mean of 432, divided by the standard deviation of 36, which will give me a z-score of 0.5. So next thing I'm going to go up here and I'm going to find 0.5, which gives me the 0.6915. But the probability says greater than, so that tells me I need to subtract that number from 1, which gives me 0.3085, or you could say 30.85%. Example 9 says, using the same information as above, estimate the probability that Jamie will be able to drive between 400 and 450. So if I look at my curve, neither number is there, so that tells me I need to do a z-score for both of these numbers. So we're finding the probability that 400 is less than or equal to x is less than or equal to 450 because it's a between statement. Then I have 400 minus my mean divided by my standard deviation, which gives me negative 0.9. If I go back up to my chart, negative 0.9 gives me 0.1841. And then we're going to do the same thing with 450, which we just did above. 450 minus 432 divided by 36 is 0.5, and the z-score associated with 0.5 is 0.6915. Now, when it's between, it's always going to be the bigger minus the smaller because you can't have a negative probability. So what we can say is that the probability that the number is between 400 and 450 is 0.6915 minus 0.1841, which would give me 0.5074, or 50.74%. This is example 10 and example 11. Example 10 says scores on a test are normally distributed with a mean of 142 and a standard deviation of 18. Estimate the probability of scoring at most 133. So probability at most means the number is less than or equal to 133. So if I create my bell curve, which I want you to pause the video and do it for yourself and then check it when it comes back, because I'm just going to put the answer on here. So once you create your bell curve with your mean in the middle of 142, adding a standard deviation of 160, so forth to the right, and subtracting it going to the left, you will see that 133 does not fall on the curve, which tells me I have to use a z-score. So the z equals the number, which is 133, minus the mean of 142, divided by the standard deviation of 18, which this gives me a standard or a z-score of negative 0.5. So if I go to my chart and find negative 0.5, you will get 0.3085. And because it's less than, I know that that's my answer. So I can either write it like the decimal of 0.3085, or I can leave it as 30.85%. Example 11 says, using the same information above, estimate the probability that a student scored at least 156. So that's asking for the probability that a student at least means greater than 156. So if we look at our chart, 156 is not on there, so we're going to find the z-score. So z equals 156 minus 142 divided by 18. Rounded to the nearest tenth becomes 0.8. So if we look at our chart for 0.8, we get 0.7881. But because this is a greater than, we know we have to take that and subtract it from 1. So we get 0.2119 or 21.19%. Last example, which is example 12, is talking about skewedness or if a normal model is appropriate. So it says that some data is not appropriate to be modeled by a normal distribution. The tail is sometimes longer on one side than the other, resulting in a skewed distribution. If you notice, if something is skewed to the left, the tail is on the left while the hump is on the right. And if something is skewed to the right, the tail is on the right and the hump is on the left. So then it says to decide if it is normal, the area under the curve from the mean to either end should roughly be half of your data. So example 12 says the lengths of 20 snakes at the zoo in inches are shown in the table. The mean is 34.1 inches and a standard deviation of 10.5 inches. Does the data appear to be normally distributed? So what I want to know is roughly half the data above and half the data below the mean. So what I'm going to do first is find the amount above, and then I'm going to find the amount below. So if I look at all the numbers that are above 34, you have 38, 39, 42, 43, 41, 39, 39, 38, 40, 37, 45, 43, 43, 37, 38, 39. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 above. And then the amount below leaves me with 1, 2, 3, 4, 5. So what we see here is that they are not evenly displaced around the mean. You have 5 numbers above the mean, 15 numbers above the mean and 5 numbers below the mean. So a normal model in this case would not be appropriate.